I'm going to talk about the Dirac Delta Function. This series of videos I'm calling a deep-ish dive into the Dirac Delta Function. You could also call it my rant on the Dirac Delta Function. We'll dive into it a little bit. And in fact, you've probably encountered it already if you've been through a few years of engineering school. And you might forget where you first learned of it. I know I did. I wasn't sure where I first learned it. You might want to wonder why we even care about it. And it's come up in several courses I've taught. I've never directly taught a course about the Dirac Delta Function. It's always been, well, we got to talk about it a little bit. But for one thing, it's a math model of impulsive physical phenomena. Some like striking a mass on a spring and damper with a hammer. There's other physical phenomena in models. When we put things into differential equations, etc., it's a possible input. I also taught the course in random processes and Kalman filtering. And the Dirac Delta Function is the autocorrelation function of white noise. And a lot of random processes are modeled as white noise going through a linear system to give us some other characteristics we like. So it's a common thing. And if you take some kind of linear system, of course, maybe control systems or signals and systems, linear systems, the response of a system to an input is the weighted sum of its impulse response. Kind of over time. You'll have to take the course to know what I mean by that, but it just comes up there in signals and systems. It's kind of comes up a lot through different systems type engineering courses. So where did we learn about it? How much do you need to know? And I'll talk about this. There's probably a reason we don't dig too deep into it when we cover it in engineering school. So let's find out where we did learn about it. How about a calculus textbook? A lot of people have to take 3 semesters of calculus somewhere before they even get to advanced engineering math. It doesn't even show up in the index. There's no Dirac in here, and no impulse in there either. It's just out of the calculus textbook. What about advanced engineering mathematics? When I taught that, that came after 3 semesters of calculus and a semester of differential equations. And it's introduced as a limit of a function. I'll talk more about this in later videos. With 2 key features, which I'll talk about in a second. And then it quickly goes on. And this shows up in the Laplace transform section of that textbook. That's the only place it shows up. For some reason, they felt the need that we needed to know that when we learned of the Laplace transform and didn't use it throughout the rest of the textbook. Here's another textbook called Advanced Engineering Mathematics, considered a bit more rigorous than the one I just talked about. And it pretty much is the same level of coverage. It comes up with 2 key properties, which I'll talk about more later. And this idea of it's a function, it's a limit of a function. So they both talk about it like this. It's a limit of a function, integrates to 1 and is ultimately 0 everywhere except at 0 or wherever you place the impulse. So it has these 2 main properties. It also has this sifting property, which they don't talk too deeply about. They don't derive it. And they don't say, well, what functions does it work on? It's kind of a lot of like unmentionables. I'll break this up right now because I want to keep my videos to about 5 minutes each.